Chapter 1 First Things First. In this chapter, we will look at the differences between hardware and software and define the principal parts of a computer. Since the computer is an electronic machine, all information it uses must be reduced to an electronic states. These states are represented by binary digits or bits. Changing sounds or images to pieces of data represented by bits is the process of digitization of information. Once information has been digitized, it can be fed into a computer and manipulated. Machine language operates with bits, while other languages need to be translated into machine language so the computer can execute their commands. You'll learn about the algorithm, which is necessary in the design of solutions to problems, and which programmers can code in any number of languages. In this chapter, important hardware components and software, the concept of digitization, binary digits, bits, bytes, the computer, an electronic machine, languages, high level versus low level, a first look at the algorithm and its relationship to programming. Introduction. Computer technology is all around us, not only on our personal computers, but also on ATM machines, fuel injections in cars, digital cameras, and telephone communications. None of this technology would be possible without computer programming. Programming provides instructions that tell the machine how to operate. In your personal computer, everything it does, from playing video games and music to typing simple documents in Microsoft Word, requires a set of instructions. This book will provide you with a basic knowledge of computer programming. It will tell you how to control the computer so that it can do something over and over again, make a decision, and store information in the right kind of holder, contingent on what that information looks like. These are just a few of the things you will learn. It is important to cover certain fundamentals before learning to program. The more you understand the machine and how it works, the easier it will be for you to grasp the concepts of programming. Hardware and software. A computer is usually hooked up to a printer, an external drive, and various other peripheral devices, such as scanners, modems, and so on. All the physical components of a computer make up its hardware. Think of the word hardware as describing those parts of a computer that are hard or can be touched. You can touch a printer, but you cannot touch a program. You cannot touch programs that are running on a computer. Programs represent software. Any programs, whether they are commercial programs, games, word processing applications, or programs that make the computer itself operate, are all examples of software. Programs are sets of steps that tell a computer what to do. there are directions for everything that happens in the computer. For example, saving a file on the hard drive occurs because inside the computer, a program is telling the computer to save a file rather than delete it. Saving a file, printing a file, or deleting it are just a few of the programs called system programs. They are also referred to as the operating system. These programs allow the computer to handle its basic operations, opening and closing files, and saving or deleting files. Likewise, getting an application such as Microsoft Word to open up and start running is the task of the operating system. Application programs are programs sold on the market, for example, WinZip, iTunes, Microsoft Office, Adobe Acrobat, Skype, and so on. The word application refers to a set of programs applied to some real-life task to make it easier to do. Some of the earliest application programs, such as Microsoft Word, WordPerfect, and ClarisWorks, were created to facilitate typing long documents. Tip: System software is the set of programs that enables the computer to store data, retrieve data, save files, delete files, and generally allow the computer to operate application programs. Let's look at a list of the main parts of a computer: keyboard, mouse, printer, hard drive, external drive, RAM, random access memory, CPU, computer processing unit. The keyboard, the mouse, and printer. The keyboard is used to communicate with the computer. So is the mouse. The keyboard is used for typed commands, while the mouse is used for clicking and interacting with the graphical user interface, GUI. The printer delivers on paper what's on the screen. Hard drive versus external drive. The hard drive is the internal memory of a computer. Application programs are saved here, as are system files. Think of the hard drive as the permanent storage space a computer has. A house with a basement and an attic has much more storage area than an apartment with only closets for storage. Computers with a large hard drive, for example 500 gigabytes GB, are in demand because of their capacity to save very large applications. MetroWorks Code Warrior, for example, needs at least 300 megabytes MB of storage space. Devices known as solid-state drives can provide more portable hard memory using flash technology. An external drive is used to expand storage capacity outside of the computer itself. As recently as the early 1990s, many personal computers had little memory in the hard drive, necessitating storage outside of the computer. Memory needed for application programs at that time was not what it is today. Although internal hard drive capacities are much greater today than in the past. There are still many uses for external drives, such as flash drives for storing pictures, video, clips, and so on. RAM, Random Access Memory. The RAM is really the workspace for the computer. Think of the RAM as a large table onto which you place many different things. If you have only a small workspace, you can't open too many things at once because they won't fit on the table. For example, if your operating system uses 128 megabytes, while Microsoft Office uses 256 megabytes, and Adobe Acrobat uses 128 megabytes, you could have both applications open at the same time as the operating system, a total of 512 megabytes, if your computer has 1 gigabyte of RAM. Now, if you run a game such as Master of Defense, you'll need another 128 megabytes just for that application. Compare that with Battleground, which requires 512 megabytes. Again, running the operating system alone with that game brings your total to 642 megabytes, and that's why you want a computer with a good size RAM, like 1 gigabyte, if you usually play such games. Opening several applications at once and not running out of memory is desirable. RAM is temporary memory and is lost once the computer is turned off. The term volatile is used to describe this memory, since anything not saved will be lost in a sudden, abrupt fashion. For example, when a plug is suddenly pulled on a machine, or if you have to reset your computer for some reason, everything in the RAM will be lost. Fortunately, there is always a backup plan for storage on a computer, and this is called a swap file. The swap file is memory taken from the hard disk space as well as from the RAM in case of an emergency. It is used only in the event that the RAM becomes exhausted and some emergency storage is needed. ROM, read-only memory. ROM, or read-only memory, is memory that's not lost when the machine is turned off. Certain instructions for the computer are permanently etched onto a chip at the time the computer is manufactured. Thus, ROM is permanent memory and is never lost. CPU, Central Processing Unit. The main part of the computer is the Central Processing Unit, or CPU. This is where the computer stores, processes, and retrieves data. The CPU manages all the functions of the computer, including processing data, manipulating data by sending it from one place to another, or by performing some math on the data. The CPU contains the Arithmetic Logic Unit, or ALU, and the control unit of the computer. The CPU is found within the system unit and should not be confused with it. The system unit houses the internal pieces of the computer, like the motherboard, the internal memory, and so on. The ALU, Arithmetic Logic Unit. The ALU affects programmers the most. When you write a program for a computer, its ALU will be called into use to perform some math, the arithmetic part, or to evaluate a decision, the logic part, by the programmer. That's why we need the arithmetic logic unit. The logic portion is the part of the unit that can handle decisions. Most interesting programs need the ability to make a decision. The control unit. The control unit of the CPU is used to regulate programming flow. The unit executes statements in sequence and will only repeat steps or skip steps if programmed to do so. If you write a program putting a number like 5 into a holder called x and decide to increase the value of x from 5 to 7, the ALU will be used to do this task. If you want to print the message "I have had enough" 250 times on a computer screen, then the control unit will have to do work because the programmer is asking the computer to do something over and over. Thus, the programmer controls how long or how many times the computer does something. In this case, printing a message 250 times. I mentioned earlier that the computer can store, process, and retrieve data, and the CPU will handle that work. Digitization, using numbers to represent information. To understand how the computer does what it does, you can examine a situation in the real world to see how numbers can be used to give information about that situation. Imagine 4 towns roughly equidistant as shown in Figure 1.1. A bad snowstorm has closed some of the roads between these towns while others are still open. Between Mapleville and Glaston, the roads are closed, as are the roads between Whittier and Mapleville. The roads between Glaston and Berkeley are open, and the roads between Berkeley and Whittier are open. If the number 1 represents the roads being open, and the number 0 represents the roads being closed, then the picture can be redrawn to look like Figure 1.2. Now you can describe the road situation using numbers. From, to, road situation, number description. Mapleville, Glaston, closed, 0. Glaston, Berkeley, open, 1. Berkeley, Whittier, open, 1. Whittier, Mapleville, closed, 0. The use of zeros and ones to describe a situation is a way of digitizing it. What was described with English words like open and closed has now been described by the numbers 0 and 1. These two digits are called binary digits, the word binary implying there are only two of them, specifically 0 and 1. The term bits is formed from the bold-faced letters of the two words binary digits. Now, let's expand on the situation of the roads. What if someone from a nearby town inquires, "Can I get from Mapleville to Glaston and from Glaston to Berkeley?" The towns surround a mountainous range which prevents driving directly from one town to the other. The answer would be no, but you could go from Glaston to Berkeley. Mapleville to Glaston is closed and Glaston to Berkeley is open. If we digitized the answer, it would look like this. Mapleville to Glaston is a 0, Glaston to Berkeley is a 1. If we dropped all English words, the answer would be in 2 bits, 0, 1. For the next question, someone asks, "Can I go from Whittier to Glaston via Berkeley?" The answer would be yes, since the roads from Whittier to Berkeley is open, as is the road from Berkeley to Glaston. Whittier to Berkeley, open. Berkeley to Glaston, open. Now, if we digitize the answer, 1, 1. The first one represents that the road is open from Whittier to Berkeley, and the second one represents the road being open from Berkeley to Glaston. Now look at an expanded map of the area, shown in figure 1.3, this time adding the names of smaller towns between the larger towns. Figure 1.3, Mapleville to Furley is closed, Furley to Glaston is open, Glaston to Crants is open, Crants to Berkeley is open, Berkeley to Rosswood is open, Rosswood to Whittier is closed, Whittier to Jackson is closed, and Jackson to Mapleville is closed. A description of the road situation from Mapleville to Berkeley via Glaston would look like the following. Mapleville to Furley is closed, 0. Furley to Glaston is open, 1. Glaston to Crants is open, 1. Crants to Berkeley is open, 1. All just the 4 bits, 0, 1, 1, 1. If you wanted to describe the road situation starting at Mapleville and going through Furley, Glaston, Crants, Berkeley, Rosswood, Whittier, Jackson, and back to Mapleville, you would be looking at these bits. 0, 1, 1, 1, 1, 0, 0, 0, which in total is 1 byte. Any sequence of 8 bits is called a byte. So the sequence we just used is a byte of information. Binary digits, or bits, can be used to describe many situations in the real world, aside from the road conditions mentioned. When these numbers or digits are used to represent a particular situation or bit of information, we have digitized information. What other examples are there of digitization? We digitize photos when we scan them. All the colors used to create images that we recognize are represented digitally. The music you hear on a CD has been digitized because musical notes can be associated with numbers as well. A password for a person using a bank card at an ATM can be digitized. In Chapter 2, I will discuss how letters and words are digitized. Note: digitizing information means using numbers to represent something other than a number. We digitized sound, color, and even images. Once digitized, they can be handled by a machine that can recognize these two integers, 1 and 0. The computer, an electronic machine. In order to be a good programmer, it is important to start with some of the fundamentals of how the computer operates. You must understand what kind of machine you're using and why it can do what it does. The computer is an electronic machine. Thus it needs electricity to operate. The electricity comes from batteries or a plug in a wall and travels through elaborate circuitry etched onto highly sensitive material like silicon on a chip. Electricity, on or off. By manipulating electricity through the circuitry on a chip, we can go back and forth between two states, electricity flowing and electricity stopped. If we assign the 0 bit to the stopped state and the 1 bit to a flowing state, these bits can be connected to the internal workings of the machine. The machine's capacity for manipulating electronic state is used to create a language of zeros and ones called machine language. It is called machine language because it is the elementary language of the machine. Without getting bogged down in the details, the computer expresses all information with these bits and bytes of machine language. Computer language. Computer languages. Languages are used in everyday life for communication. All of us speak a native language, and depending on how much we read or write, we can develop a deep understanding of that language. The important thing about language is that you use it effectively to communicate your intentions, needs, wishes, or feelings. Computer languages are similar to spoken languages in that you must use them very precisely so that you are not misunderstood by the computer. Each language has its own grammar or syntax, which must be followed for the computer to understand that language. Consider these examples from spoken languages. English: hello, how are you? French: bonjour, comment va bien? German: guten Tag, wie geht's? Japanese: konnichiwa, o genki desu ka? All of these examples mean the same thing. Each sentence has a greeting followed by a question, asking how you are. But each example is a completely different group of words. Unless you know these languages, you would not know that each means the same thing. Computer languages are similar in that there are basic tasks that any computer language must do for a programmer. The programmer just has to learn to speak the language. One advantage of a computer language over a spoken language is that it does not take that long to become fluent in a computer language. Many programmers learn several languages during their careers. Now read these examples from some computer languages. Basic. If x is greater than 5, print greater. Pascal. If x is greater than 5, then write ln greater. C++. If x is greater than 5, C out less than greater. Java. If x is greater than 5, system.out.println greater. All of these statements accomplish the same task if the contents in the variable called x is greater than the number 5. Then we will print a message on the computer screen, the word greater. Levels of language, high and low. All programming languages need to be translated into machine language, the native language of the computer. Machine language is comprised of binary code and therefore is extremely tedious to read and understand. Since the computer can only execute commands that have been written in its native machine language, other languages must be translated into machine language before being understood by the computer. There are two levels of languages among programming languages: high-level languages and low-level languages. High-level languages. High-level languages are languages that are high above the language of the computer. It's machine language, the language it understands most naturally. High-level languages are removed from the reality of how computers process data, that is, in terms of bits. They are as removed from machine language as a king or queen is removed from the everyday worries of life, like making money, paying bills, and so on. Machine language is made of all binary digits, but high-level languages use English words to give directions to the computer. In order to understand the phrase high level, consider first the following analogies. Let's say you want to have a party for over 100 people. A high-level party giver would simply pick a date for the party, invite friends via email or the telephone, and then the party would take place. A low-level party giver would have to handle all the details, that is, renting a place, hiring a caterer, a band, and so forth. The party would not just happen. You would have to deal with all the details, which the well-heeled high-level party giver can ignore. Suppose you need to get your car fixed. A high-level approach to repair would be to bring the car to the repair shop and pick it up when the work is done. A low-level approach would be to lift the hood yourself and examine the parts, looking for the problem. Once the problem part was found, you would have to repair it yourself and then close the hood. These analogies apply to programmers as well. The high-level languages programmer doesn't need to know anything about how the computer itself goes about its work. He states a problem at a higher level without being involved in its nitty-gritty of how the computer performs its tasks. For this reason, high-level languages use commands that relate directly to the problem being programmed, as opposed to the internal workings of the machine. Programs written in high-level languages run much more slowly on the computer because these languages need to be translated into machine language. Languages are defined in terms of their proximity to machine language. The higher the level, the more translation required before the program can be executed by the machine. Programs written in a high-level language require fewer lines of code than those written in a low-level language. It's much easier to say, "Let's give a party," or "fix the car," than say, "call the caterer, order food, rent the hall," and so on. Pascal, COBOL, Fortran, BASIC, C, C++, Perl, and Java are some examples of high-level languages. Note: computers understand machine language, which is generated from the electronic states determined by the current and circuitry of the machine. Low-level languages. Low-level languages are just above machine language level. As such, they do not undergo as much translation as the high-level languages. They are, however, more difficult to understand because they rely on a greater understanding of the internal workings of the machine. Assembly languages are low-level languages. To a basic programmer, C might be considered a low-level language, since it allows the programmer to have more control at a lower level than the basic programmer. Language helpers, translators. Translators break down high-level and low-level languages code into machine languages understood by the particular processor in the CPU. There are two kinds of translators: interpreters and compilers. Interpreters and compilers. Translators can work in two different ways, as interpreters or compilers. Interpreters will translate one line of code at a time and generate error messages immediately. Compilers translate an entire file of code all at once, rather than line by line. The compiler will not generate error messages until all code has been translated. The original file or program that the programmer writes is called source code. Object code is the result of the translation and is the machine language version of the original file. C++ is an example of a compiled language, while BASIC is an interpreted one. Note: Translators can change high-level languages or low-level languages into machine language that is readily understood by the computer's processor. The algorithm, the basis for all designs to solutions of programming problems. We are almost ready to begin the subject of programming, taking problems in the real world and writing them in a language that the computer can understand or execute. Before you get to the stage of programming your problems, you must design a suitable way of solving problems. An algorithm is the set of steps for solving a problem. These steps may repeat and may involve decisions, such as a choice of two or more things. Consider the following example of an algorithm for buying a ticket to a movie. 1. Go to the theatre. 2. Walk to the ticket counter. 3. Select a movie. 4. Pay the price. 5. Receive the ticket. What about an algorithm for finding the smallest number among three numbers? 1. Compare the first number with the second number. 2. Discard the biggest number from step 1. 3. Compare the third number with the number that's left. 4. Discard the bigger number from step 3. 5. Whatever number is left is the smallest of all three. The three parts of any algorithm. An algorithm has three parts. 1. The steps are finite, i.e., they do not go on forever. 2. Steps may be repeated. 3. Steps may involve decision-making. Tip: each step of an algorithm should follow the step before. If necessary, repeat some of the steps and skip others if a decision calls for that action. Examples of algorithms in the real world. Some examples of other algorithms follow. Buying fries at a Burger King. 1. Select the size of fries that you want. 2. Take out enough money to pay for them. 3. Hand over the money. 4. Receive change if necessary. 5. Take fries with you. Dialing a friend who lives locally. 1. Pick up receiver. 2. Dial 7 digits. 3. Wait for friend's voice. Programming a VCR's timer to tape a show. 1. Select menu button on remote control. 2. Select program menu from the given menu. 3. Complete table information about program's start time, finish time, channel, and speed of programming. 4. Press menu button on remote control. 5. Press power button of VCR. 6. Check for red light on VCR. Programming. Now we are ready to discuss the subject of programming, taking a problem or task and designing an algorithm to handle this task, then using a programming language to express that algorithm so the computer will be able to execute that code. Most people think of programming as being just about code, the lines of symbols and words that all of us have seen if we have ever opened a book on programming. It is more than code, however. It is a way of thinking about a problem and designing a solution that can then be written in a programming language. Look at this short C++ program that prints the message, "Could you please say that again?" 250 times on the machine. # include less than IOStream. # include string.h. int main parentheses. Int x semicolon. String first phrase semicolon. First phrase equals, "Could you please say that again?" For x is equal to 0, x is less than 250, x plus plus. C out, first phrase and out, return 0. Here is another version of the same program in Pascal. Program print message variable x colon integer semicolon first phrase colon string semicolon. Begin first phrase is equal to, "Could you please say that again?" For x colon equals 0 to 250 do begin write ln first phrase x colon equals x plus 1 semicolon end. Each of these examples could have been written in any language. The main point of these programs is that they both contain a loop, which is another way of saying that a particular task is being executed over and over again. The point of showing both of these programs is to focus on how they are similar rather than the language differences. As you move through the chapters that follow, keep in mind that languages will always change to suit the development of technology. Certain concepts remain the same regardless of language. If you learn these concepts well, you will have no problem becoming a serious programmer. Summary. We looked at the basics of the computer, including its hardware and software. We examined the computer as an electronic machine that can recognize changes in states of on and off. These states represent the basis of the digitization of information for the computer. Programming relies on the ability to write clear step-by-step solutions called algorithms in a language. Some languages are high level and easy to use, while other languages are more difficult to learn because they are low level and closer to the machine's understanding. In Chapter 2, we will look at the first major concept of programming, understanding variables.